take it away.
Okay, so yeah, so I'm very happy to take questions. So like interrupt if anything's unclear or you want more details. Yeah, so I'm going to talk about local crushing. And the crushing part of this is maybe not old in the scale of things, but it's not new. So that's kind of the plan. This is the first half of the talk. I'm going to sort of motivate and introduce crushing. I guess there's kind of a lot of, or I guess quite a few sort of different interconnected ideas that kind of go into that. So possibly the first half of the talk is more like the first 2/3 of the talk. So we'll see how that goes. And then in the second half, what I'll talk about is a sort of new perspective that I'm working on. So this is very much, it's work in progress. If anyone, like, don't be holding your breath for like a new theorem or something at the end of the talk, because that's not happening. It's not to that stage of finished yet, but I guess the reason I wanted to talk about this is just because this just seems like a very promising kind of approach. So here goes. How should I start? So maybe I start by yeah, I guess I want to talk about a problem that, yeah, so crushing you can use to, it's now known that you can use to solve for lots and lots of problems. So maybe like the best motivation is just show you how it can be used to solve a problem. So I'm gonna choose unknot recognition as the problem and sort of try to explain how crushing gives us a solution. By solution, I mean an algorithm for unknot recognition, and not just an algorithm, but an algorithm that is pretty effective in practice. So you can actually, like, this is coded up, and you can run it. So what is unknot recognition? The idea is you embed. I mean, a knot is an embedding of S1, so embedding of a circle in S3, which is sort of kind of, if you've never seen S3 before, then it's sort of kind of R3 union a point at infinity, right? So basically you can think of it as it's an embedding of a circle in R3. So I should draw some examples. So here's an example, a very boring embedding. Here's another example. So what's happening here is, like, I've drawn a gap, right? And that's basically just to indicate that this bit is passing over the bit with the gap in it. Okay, so there's another example. So yeah, as you can see, I have no slides prepared. So what this is going to be is going to be 45 minutes of me drawing pictures for you. I can draw a better trefoil knot than that. There we go. I passed the test. I'm a real topologist because I can draw knots. Yeah, so here are some examples of knots. And I guess one sort of very natural thing to ask is, if I give you some knot, can I untangle it, right? And basically what I mean by untangle is, can I move the knot around in space and turn it into this boring example? Yeah. So maybe it's not so hard to see that this one you can untangle, and I claim that the other two you cannot untangle. Yeah, so this is the problem we're trying to solve. I give you a knot, or I give a computer a knot, and I ask the computer, can I untangle this knot? Can I move it around in space and just get back a plain, boring old circle? And this is maybe a little bit, I don't know, maybe this seems like a bit of a nebulous thing. Like, how do you tell a computer to do this? Or even just make a computer understand the problem? So let me sort of, yeah, one way to do this is kind of, if I want to, okay, so we're going to sort of do a few steps to try to make this more kind of concrete so that we can get a computer to understand it. So one is the way I'm going to characterize something being untangleable is that it bounds, so the knot bounds a disk. So if you look at the trivial example, right, clearly this knot bounds an embedded disk in S3 or in R3. And so the claim is that this is an if and only if. So if you bound an embedded disk in R3, you are the unknot. Maybe I should say anything that you can untangle is called the unknot. And if you are the unknot, then you bound a disk. So here's the disk in this example. So like, maybe this is a bit hard to visualize. It's basically just like a saddle shape, right? Yeah. So what we're going to do basically is somehow get a computer to search for this disk. And if the computer finds the disk, it's the unknot. And if it doesn't find the disk, it's not the unknot. That's the idea.
Hey, Alex,
this,
question.
Yeah.
So this is this like classically how you define whether something is the unknot? Or is this like a new thing?
I mean, this is not new either, but I guess if you wanted to define it, you'd say there's an ambient isotopy, blah, blah, blah. And then you can prove that that's equivalent to the existence of this disk. It's not so hard. Like if you have a disk, right, you can kind of just shrink the knot through the disk. And like, because it's a disk, eventually, once it becomes small enough, you'll see that it just becomes a circle.
Yeah.
And then if you have the unknot, I guess if you have this unknot, it's obvious that there's a disk. And then if you have a different unknot, there's like an ambient isotopy that takes that different unknot to the trivial, like boring one.
Yeah.
And you can sort of follow that disk through the ambient isotopy. So
right.
The disk will be there.
That makes sense.
Yeah. But that's a good question, and probably important. So thanks for bringing that up. Yeah. Okay, so we're looking for the disk, but I guess maybe this doesn't seem any more helpful for inputting into a computer. So okay, so the first thing is we want to bring in kind of all the machinery that comes with properly embedded surfaces. So what we're going to do is once we start looking for the disk, we sort of don't care about the knot. We care about what's happening somehow away from the knot, right? Because somehow the disk is sitting outside the knot. So what we do is, so remember our knot it's K, it's sitting inside S3. And what we care about is what's happening outside the knot. So we take what's called the knot complement, which is just S3. And I'm going to say minus a neighborhood of the knot, which I'm going to write like this. So you delete a neighborhood of the knot, a small kind of, so what does that look like? I can't really draw this. So you basically take like a little torus neighborhood, right? And you, whoops. So this is like meant to be, this is a terrible drawing, but maybe this gives the idea. Right, a little solid torus neighborhood of the knot, you delete that. And what you get left with is a manifold with boundary, which we call the knot complement, and it's basically the space that's sort of away from the knot. And the claim is that this disk this disk that I'm talking about here, that exists if and only if there exists a disk in the knot complement. So let me write this in shorthand. If and only if there exists a copy of D2 in the knot complement. And what we want, right, is the boundary of this disk. Okay, so there's boring disks where the boundary is just like that, right? And that doesn't tell you anything, right? So what we want is the boundary of this. Sure, let's write in purple. The boundary of this d squared is non-trivial. And by that I mean, like, once we've deleted this neighborhood of the knot, we get some torus boundary, and we want a non-trivial curve on that torus boundary. That's what we're looking for. Does that? I mean, if that doesn't make sense, please interrupt.
So the boundary of the disk lies on the boundary of this.
Yes,
knot
yes,
complement?
we insist. Yes. Yeah, sorry, I said that in words, but didn't. So we want the disk to be properly embedded, which just means that the boundary of the disk lies on the boundary of the manifold. Yep. So we're looking for a non-trivial boundary curve.
Sorry, Alex.
Yep.
Can you say again what you mean by non-trivial boundary? Like, it's not just that it's non-empty. It's not just like a circle.
I mean, it will be like it's a closed curve, but we want it. Well, I suppose it's homologically non-trivial, if you like. I mean, probably there's lots of equivalent ways to say, but homologically non-trivial in the boundary surface.
Yeah,
that's one way. Yeah. I just don't want a circle that you can like contract. Yeah. Okay. So what we're going to do now, because we want to do computation, is we're going to triangulate. I'm going to triangulate Hagar. Right, because this will give like a discrete and finite representation of this knot complement. By the way, this is why I want S3 and not R3, right? Because S3 is compact, and therefore you can triangulate with a finite number of tetrahedra. So maybe I should say the way I'm going to describe triangulations is, I mean, it's just a collection of tetrahedra. And the way you describe a triangulation is just say like this face is glued to this face in some order. Like you're allowed to like rotate things, but it's a very combinatorial thing, right? You just say, here are the faces that are glued together, and you can stick that into a computer. Maybe that's all I need to say about triangulations. And so now what we're looking for is an embedded disk with the right properties inside a triangulation. So now we need a discrete representation of embedded surfaces. So here we go. I'm racing through lots of different concepts. Normal surfaces. So what these look like, basically the way it's defined is you look at how a surface intersects each tetrahedron in isolation. Maybe I shouldn't redraw it every time. I should just do this. Tablet magic, right? So what we want is the intersection with each tetrahedron is a collection of disks, and the disks come in 7 types. So there are these 4 triangle types. So each of the triangles just slices off a vertex, and you have 4 quadrilateral types, which I should take care to draw properly. So we insist that our normal surface, our surface, for it to be normal, it has to meet each tetrahedron in a collection of disks that look like one of these disks that I just drew. So you could have many quadrilaterals and you could have many triangles, but it has to be, for example, you can't have something like this. It's like a little degenerate parachute thing that kind of just sitting on one edge. What do I want to say about normal surfaces? Well, I guess, how do you tell a computer, or how do you get a computer to encode these things? Maybe that's what I should talk about. Yeah, so what I'm going to say is, if you look at one tetrahedron at a time, you can sort of start to give things coordinates. So what I've drawn here is there's 4 triangle types, and in this particular picture, I've drawn 1 triangle of each type. So this is kind of natural way to represent this. You just say, well, right, you just write down a vector with like 1, 1, 1, 1 that says there's 1 triangle of each type, and 0, 0, 0, 0, which is saying of the 3 quadrilateral types, we don't have any of them, right? So maybe I don't. Right, you have zeros and then 1, 0, 0, and here you have zeros for all the triangles, and say 0, 1, 0, etc. Right? The etc. skipped one thing, but so let me give one more slightly more interesting example. I don't know. So let's say it's a triangle here, a triangle here, triangle, maybe a triangle, and let's say 2 quads, right? Yeah, so what this would look like in coordinates is you've got 1 triangle, 1 triangle that cuts off that vertex, 2 triangles that cut off this vertex, 1 triangle that cuts off the vertex on the left. For the vertex on the right, there are 0 triangles. And then, what did I say? The quadrilateral, so these 2 quadrilaterals are of this type. Yeah. So I have 2, 0, 0. Yeah, so there's a natural way to give coordinates to these things. And so what you get is every normal surface S becomes a vector in R to the, well, integers, right? So it's going to be Z to the, you get 7 coordinates for each tetrahedron and n tetrahedra, so 7n coordinates. So that gives us a coordinate representation, but and the computer, I guess, is going to be working with these. There's a problem here, right? Which is if I just give you a vector in Z to the 7n, does that give a normal surface? And the answer is not always, but there are some easy constraints that tell you when. So maybe, how do I go back in the other direction? There are some easy constraints that tell you exactly when a vector in Z to the 7n is represents a normal surface. So let me just list them. So the first one is obvious. All your coordinates have to be non-negative, of course. The second one is basically, well, okay, so let's say I have these 2 blue triangles are glued together, right? So there's like a tetrahedron on either side. And they're glued together And let's say I don't do any rotations and they're glued together somehow, just straight on, just to make the drawing easier. Let's say I've got, well, okay, so let me, All right, so let's say we have this in the left-hand tetrahedron. Okay, so what we do is we look at these two arcs, right? Because the two triangles are glued together, if you have those two red arcs, you've got to have whatever you have in the right-hand side tetrahedron, you've got to have those two arcs. So maybe it's these triangles, for example. And the purple arc, you also have to have a purple arc here, and maybe that's a quad. Who knows? So the way you write this down is, let's say, okay, so let's say T0 represents the number of triangles of this type, and Q0 is the number of quadrilaterals of that type, and T1 is the number of triangles of this type. I mean, the equation says basically, so you have an equation basically that just says this, right? The numbers of these things have to be equal, T1 plus Q1, where Q1 would be the quad in the right-hand side triangle that meets in an edge of that type, which in this case, there are none of, right? So in this case, we've got 1 plus 1 is equal to 2 plus 0. Okay, and we construct a whole bunch of equations in this form. That needs to be satisfied. So this is also, I guess I'm going through necessary conditions here. Necessary conditions for a vector to represent a normal surface. And maybe one thing I will point out here, these are linear equations or linear inequalities. This is important. I'm spending way too much time on this. So, these are linear inequalities. Okay, so the third condition, I'm gonna write the name and then I'm going to talk about them. So these are the quadrilateral constraints. And I'm going to go back to my pictures of the quadrilaterals to explain this. So basically the idea is each of these quadrilaterals cuts the tetrahedron in half and separates a different pair of edges. And the pair of edges is the red ones that I'm highlighting. So what does this mean? It means if I have, let's say, quadrilaterals of these two types, I have one quadrilateral of type A and one quadrilateral of type B in the same tetrahedron. And because they kind of cut the tetrahedron in half in different ways, right? There's no way, well, so this quadrilateral, so quadrilateral B goes from, it touches like the two halves that are split apart by quadrilateral A. So therefore, there's no way to arrange for these quadrilaterals to be disjoint. And therefore, you couldn't have an embedded surface from that. So the quadrilateral constraints say that if you have any quadrilaterals at all in your tetrahedron, they all have to be the same type. Otherwise, you can't have an embedded surface. So that's a necessary condition, which is, this is nonlinear, which is important for computational reasons, but possibly I won't have time to actually really say why. Okay, these are a bunch of necessary conditions and claim is they're sufficient. And I'm going to skip saying anything about why. Okay, so we have conditions on what a normal surface is and how they look in coordinates. I don't know what I just said. Maybe I should quickly do some examples. Okay, so one example of a normal surface that always exists. So I'm looking at a vertex here. I can always like make a really small triangle. It's really close to the vertex. And if I look at a tetrahedron that's kind of next to this one, I can always put another really small triangle next to it. Right, and I can just keep building up a bunch of these triangles. And what this does is it triangulates the boundary of a neighborhood of the vertex. Right, so what this is going to be is it's going to be, if you have a vertex in the interior, right, this is going to give you a small sphere. If you have a vertex on the boundary, so like I guess this is the boundary and all the other purple stuff is the interior of the manifold. Here's your vertex on the boundary. You'll get like a little disc that kind of like a bowl that kind of surrounds it. And these always exist, right? Clearly these always exist. So these are trivial normal surfaces, and we're going to basically ignore these because they always exist. And basically the distinguishing characteristic of these is they're completely built out of triangles. And if you build something completely out of triangles, it's going to look like one of these. So what does non-trivial mean? Non-trivial just means you have some quadrilaterals. Okay. Now I'm going to make a claim, which I won't have time to justify, which is we're looking for a disk, right? We're looking for some embedded disk. And the claim is if the disk of interest exists, yeah, I'm not going to justify this, even though I'd love to. Then we can make it normal, basically. We can make it normal. So your algorithm basically looks for one of these disks in normal position. And you're guaranteed that if it exists as like some embedded surface that may or may not be in normal position, you will find one that is in normal position. So basically what I'm saying is restricting our attention to normal surfaces doesn't lose any information. So this is safe to do, or at least it does lose information, but it doesn't lose the information we care about. And I'm not going to justify this. So we're looking for a disk, and it turns out that, well, okay. I'm racing here, racing the clock. Okay, so I'm going to say we're looking basically for a surface with Euler characteristic 1. A normal surface with Euler characteristic 1. And I'm saying it this way, again, because Euler characteristic is a very combinatorial thing that you can give to a computer. But you can express this also as a linear constraint in the coordinates that I mentioned before. But it's not homogeneous, right? Because of the 1. And this is bad because we're trying to, roughly because we're trying to solve for some linear constraints over integers. And this is sort of like if I give you a bunch of linear equations, right? And I ask you to solve it over real numbers or rational numbers, like somehow that's easy to do. But if you insist on integer solutions, it turns into number theory and like it's much harder, right? So what we do is we replace this with, so we don't want this. We replace this with Euler characteristic positive. And what this means is if you find a rational solution, you can scale it to a positive integer solution. And so this turns into like somehow an easier problem. So now what this means is we're looking for, after all that, we're looking for disks, right? Disks fall into this, or spheres, right? Because spheres have Euler characteristic too. What else has positive Euler characteristic? Projective plane, but that can't appear because we're in a knot complement, which is a submanifold of S3. Right, so we can't have projective plane. So this is it, or I guess disjoint unions of these things. But I claim that we can just, I mean, we can make sure that what we're finding is always connected. So this is it. And the problem is, we've solved one problem, like we've made the problem somehow easier by turning this into looking for rational solutions, which that solves some things. But now we have these spheres, right? Like, what do we do if we find a sphere? And that's where crushing comes in. So we crush the spheres basically. And this is getting very sketchy, but we crush spheres. And what this does to your manifold. So here's the boundary of your manifold, right? This is an awful cartoon, right? Here's the torus boundary of your manifold, and here's the manifold. So this is K bar, and here's your sphere. So this is S2. This is somehow a normal sphere embedded in your manifold, and because we're inside S3, this bounds a ball. And what crushing does is it says we quotient the entire sphere down to a single point. So the cartoon of this is boundary stays, and then you get somehow this, right? Right? Your sphere becomes that single green point. And because this sphere is somehow topologically trivial, it bounds a ball. What happens on the left-hand side is you still got the knot complement here. That topologically is unchanged. And on the other side, okay, so what have we got? On the other side, we've got a ball, and we've quotiented the boundary of the ball to a point. So on the other side, what we've got is S3. Okay, so topologically, what's happened? Topologically, really what's happened is we've kind of cut along the sphere, right? So you cut along the sphere, which gives you this, right? So this is K bar minus a ball. And we've also got, right? We cut along the sphere, and then we filled those two boundary spheres with balls, topologically. That's what we've done. So we've undone, probably people here know what a connected sum is. So we've undone a connected sum, but in this case, a trivial connected sum. That's what we've done. That's great, but we have a problem, which is what happens in the triangulation, right? In the triangulation, I don't know, say we've got something like this, right? Because of the quotient, all of these triangles and quads, they become points, right? So when we crush, they become points. So we have something like this. So the triangle becomes this point. And what do we have going on? Something like, works better. Something like this. Anyway, the point is, this is not a triangulation. So we've done some bad things, okay? And so what we do, by the way, this is supposed to say crush. So what we do to recover a triangulation is we turn all the non tetrahedron pieces into something that could appear in a triangulation. So basically, this little football, like rugby ball looking thing, that goes down to an edge. These little fat triangles, we just turn into, triangles. We get two triangles here. Right, so we flatten everything down. And the claim is that this is, I mean, if you're looking at this, probably you have a right to be nervous because this could start doing topological things, right? This will change the topology of your manifold. But theorem, it's not too bad. There's not that much that can happen. And partly this is because we're in a submanifold of S3. But yeah, I'm skipping details. Okay, so I claim you can reconstruct a triangulation eventually. Okay, so eventually get a new triangulation of K bar. And so that's roughly the algorithm. If you find a sphere, you crush it, you get a new triangulation of K bar, rinse and repeat. And what happens is every time you crush, the number of tetrahedra decreases strictly. So you can't just keep finding spheres forever. You have to stop at some point, which means at some point you find a disk or you prove that there are no spheres or disks at all. And then your algorithm is done. So that's crushing. And that was the first half of the talk, which is the first 90% of the talk. So let me take a few minutes to say what's happening with this local perspective. I need to, okay, let me copy this because I kind of need this picture. Yeah, so when you have a quad in the tetrahedron, what you see is there are no tetrahedra left afterwards, right? This is why when you crush a non-trivial surface, your number of tetrahedra strictly decreases. Because every time you have a quad, what you get afterwards is no tetrahedra. So what happens if there are no quads? Okay. Let me just draw a really boring. So like there's just one triangle, right? So what happens when you crush this? Right, you'll still get this same, you get this football, right? And now you see what's left is like a smaller tetrahedron, right? So if you have no quads, the tetrahedron survives somehow. So in the new triangulation, basically you have, well, okay, so for every tetrahedron in the old triangulation, there's either a new tetrahedron in the new triangulation, or the old tetrahedron was destroyed. And that just depends on whether you had a quad or not. So this is why the numbers of tetrahedra strictly decreases. But the point is, somehow, after you go through this whole rigmarole of finding a normal sphere, you don't really care about the sphere. Somehow, you just care about where the quads are. You don't even care about how many quads there are. You just care about which quads there are, right? You don't really care about the sphere. So somehow it smells like there should be something you can say just by looking locally, one tetrahedron at a time. And that's a very vague picture of what I'm trying to do here is what happens if you, instead of searching for a normal sphere, because despite all the optimizations I talked about with, making things linear and homogeneous and so on, theoretical bounds still say this is exponential time to find a normal sphere or prove that it doesn't exist. So we want to avoid that or find a way around that. And so the idea basically is to try to understand, instead of finding a sphere, try to understand what happens when you crush one tetrahedron at a time. and see, like, try to describe that topologically and see if that either kind of gives some insight into, I mean, there's sort of different directions this can go. Either this directly tells you, gives you a way to say, I should crush these tetrahedra in these directions. Or maybe it tells you something about whether a normal sphere exists without having to go through the whole exponential time algorithm. So it's really, I mean, without saying more, it's a little, probably this is like a good place to finish and just say, yeah, so we have this crushing machinery, which is really, basically, so this is a summary of the talk, I guess. We have this crushing machinery, which is really good. The problem with crushing is you have to find a sphere or disk. And this is a hard problem. Finding the sphere is a hard problem. And so we're trying to avoid that, basically. We're trying to find a way to circumvent this. And the kind of really tantalizing thing about crushing is exactly that somehow when you crush, like when you actually do the crushing, you don't care about the sphere. You just care about where the quads are. And so that's kind of roughly the motivation. Yeah, so thanks for listening.
Thanks, Alex. If you can unmute and clap, that would be even better than an emoji. Does anyone have any questions?
Yeah, so okay, so this is a good example with the like unknot recognition, but what are some other algorithms and applications where like not just crushing, but like especially this sort of local crushing idea may be useful as well?
I guess, okay, so if, I mean, there's a big if here, but if local crushing goes somewhere useful, then it should be useful anywhere that crushing is useful. And so I'm going to answer your question by saying some other things where crushing is useful. Maybe, okay, so I'm going to go back to this sphere cartoon, right? So what I said is when you crush a sphere, you're basically undoing a connected sum, right? So another problem that you can solve with crushing is connected sum decomposition. I give you a manifold, and you have to give me back the decomposition into prime manifolds, right? And the way you do that is you find a sphere and undo the connected sum, which basically means do the crushing. There are details to take care of here because when you recover a triangulation, things can happen, but basically that's the algorithm for connected sum decomposition. I guess in my abstract, I mentioned three-sphere recognition, but that involves a generalization of normal surfaces called almost normal surfaces. So I won't be able to say more about how that works without talking about almost normal surfaces. So that's where crushing has been implemented. And then I guess more generally, there are a lot of, I mean, that's really the core of it. That's where crushing is really been implemented as useful algorithms. But normal surfaces more generally give lots of algorithms, and probably you can adapt crushing to work for those. Well, okay, so here's an example, in the last 2 weeks, I implemented handle body recognition. Yeah, so Ben, it's just put it in the chat. I implemented handle body recognition, and this also is done by crushing. And the idea is you look for spheres and disks. If you find a sphere, right, because it's a handle body, it's still a trivial sphere. So we have the same picture. Crushing the sphere basically doesn't really do anything topologically. If you find a disk, crush the disk, right? What that does is it cuts along that disk, right? So what this does either is basically, well, if it's a separating disk, then it cuts your handle body into two smaller handle bodies, or it reduces the genus. It's one of the two things, right? And so you just keep doing this, right? there's a complexity that will decrease every time you do this, right? Either you cut it into smaller pieces or you reduce the genus. And so you just keep doing this until you stop. And either you prove that you had a handle body, or you get to a point where you can't find any more of these spheres or disks, which means you're not a handle body, basically. So yeah, so there's lots of applications of crushing, and therefore, if local crushing goes anywhere, then there's lots of applications for local crushing. And hopefully what this, I mean, if local crushing really goes anywhere, then it means we have maybe faster theoretical bounds for crushing, or maybe even faster algorithms, full stop. This is all speculative, but that's why I say, like, this is an exciting sort of idea.
Thanks.
Are there other questions now? I can stop the recording if people want to ask unrecorded questions.
Alex, I have a question. We
Okay, go
have
ahead.
here this problem of unknot, and we also have the software. I think it's called Snappy. So I'm wondering if Snappy helps to solve this problem.
Oh, if Snappy, so Snappy doesn't do normal surfaces. So I don't know. I've never used.
I mean, for the general problem, not really more about the general surface. Like, in a such a way, does it help to solve this problem of recognize the unknot?
I don't know. Does Snappy have unknot recognition? Does anyone know? Right, the hyperbolic case. So Ben says Snappy helps in the hyperbolic case, because that's really right, because that's what Snappy was designed to do, is hyperbolic manifolds. So I guess this, sure, if you have a knot and you know it's hyperbolic, well, if you know it's hyperbolic, it's not the unknot. So but okay, so with knots more generally, if you have a hyperbolic knot, then Snappy, sure, Snappy will tell you lots. If it's not hyperbolic, I guess Ben says.
Yeah, in practice, Snappy, I mean, it calculates fundamental groups, even if it's not hyperbolic. I don't know how the precision is when it's not hyperbolic, but definitely, like, in my use of Snappy, I can at least see something about a non-hyperbolic knot by looking at the fundamental group, and if it's what you expect for an unknot, then I typically trust Snappy that it's an unknot. But yeah, definitely it's intended for hyperbolic manifolds. So.
Yeah, so I guess maybe the answer is Snappy does some things, but if you want to, 100% guarantee this is the unknot or this is not the unknot, unless it's hyperbolic, then Snappy can say this is not the unknot. Yeah, probably you need something else like Regina. And Regina will do it. Does that answer the question?
Thank you. Yes, thank you very much.
Okay, well, let's thank Alex again, and we'll stop the recording, and then people can hang around a bit longer if you want to.